Hi, welcome back. This is question number 6 from the BC 2021 Calculus AP exam. They give us a function g, and it has derivatives of all orders for all real numbers. The Maclaurin series, so they tell me it's Maclaurin, which we know we like Maclaurin, as tell us that the center is at 0. Given by g is this series on its interval of convergence. Now the first question says, state the conditions necessary to use the integral test to determine if our series here converges. And then they want us to use the integral test. Now typically for this one we would probably use geometric series, but they want us to use the integral test for this one. Alright, so let's see here. Alright, so what does it say? It wants us to use the integral test. Well, we would say, well, we're going to let f of x equal 1 over e to the x. Now, since it's 1 over e to the x, we know that f of x is continuous. It is decreasing. It is, well, positive and decreasing. Now, because it meets all three conditions, we can now say that the antiderivative from 0 to infinity of 1 over e to the x. The answer to this integral will give us the answer to our series. Now this is improper, so we're going to write it as improper by using limit notation. The limit as b goes to infinity from 0 to b, 1 over e to the x dx. Now if you've forgotten, this is just really e to the negative x. So if I integrate that one, we would get negative the limit as b goes to infinity of e to the negative x from 0 to b. The negative came from our u substitution. U would become negative, so that's where that negative came from. Using the FTC, we would get the negative the limit as b goes to infinity, and this becomes e to the negative b minus e to the 0, which is just 1. Now, if we let b go to infinity, of course, this just becomes 0. E to the negative infinity is 0, and that, of course, just becomes 1. So what we're left with is we've got this negative here, and we got this negative 1, which is 1, and this is finite. Therefore, what we can say is that the integral converges. The integral converges to 1. And now, because the integral converges, we can now say the series converges because the integral converges. And this is by the integral test. Even though they told us to use it, I'm still going to write down what test I used. By the integral test. Alright. Now, part B says, use the limit comparison test with this series to show that this series here converges. Now, this is an alternating series, so I already know that this converges. So we want to know if this series converges absolutely. So the first thing I'm going to do is I'm going to use my alternating series test right here. Okay? That I know that this will converge by alternating series. So the series alternates, decreases in magnitude, and the limit equals 0. Therefore, the series converges by alternating series test. Alright. So I'm just going to say that it converges. They may not want it, but I'm going to put it out there anyways. Next, we want to find it. Now they tell me to use the limit comparison test. Now we already know that the integral, so step 1, I'm going to say that the series, 0 to infinity of 1 over e to the n, this already converges. We already know that because we did the integral test by integral test. We already showed that. So step 2 says to do the limit comparison now. So remember, when I'm trying to show something converges absolutely, we want to make sure that if this was all positive, will this converge? And that's what the limit comparison test is going to kind of help us out with here. So the limit as n goes to infinity, using the limit comparison test, we would take our magnitude here. We want the magnitude because we want it absolute. So we don't really care that it alternates, so we get this 1 over 2 e to the n plus 3 times e to the n over 1. And if I do this, we're going to get 1/2 as n goes to infinity. So this is finite and positive. Therefore, we know that the series converges by limit comparison. By limit comparison. So what does that mean? Well, remember, we wanted convergence absolutely. I've already established that this will converge. I've already established that this will converge. And now we use the limit comparison to determine that the magnitude of this will actually converge as well. So because the series, the original alternating series converges, and the series converges by, if it was always positive, if you remember right here, this is just all the positive values, also converges. Therefore, we can say that the series from 0 to infinity, -1 to the n over 2 e to the n plus 3 converges absolutely. And the last part C says, determine the radius of convergence for our series. So that's just our ratio test here. So this is our ratio test, radius of convergence. So we would set the limit as n goes to infinity of -1 to the n plus 1. And the series, remember, will have this x right up here, which is the series, so that's going to become x to the n plus 1 over, and over here this is the really tricky part, 2 e to the n plus 1, 2 e to the n plus 1 plus 3, divided by its inverse, 2 e to the n plus 3 over -1 to the n times x to the n. And we want to make sure that that's less than 1. Simplifying this, the limit as n goes to infinity. The -1s really don't matter. That's just going to become 1 because I'm taking the absolute value anyways. So what we're left with is this x, just x, times 2 e to the n plus 3 over 2 e to the n plus 1 plus 3 is less than 1. So when I factor out my x, we're going to get this x right here. So I'm going to get to the absolute value of x times, and what I'm left with is this part right here, the limit as n goes to infinity of 2 e to the n plus 3 over 2 e to the n plus 1 plus 3 is less than 1. And I want to find out what this is. I don't know what that is. So what I'm going to do is, I'm going to do that over here real quick. So we get the limit as n goes to infinity, 2 e to the n plus 3 over 2 e to the n plus 1 plus 3. Now as we go to infinity, this 3 doesn't matter. Too small. And neither do the 2's. So what I'm really left with is it's e to the n over e to the n plus 1. And that just becomes 1 over e. So what I'm left with now is just the magnitude of x over e times the limit as n goes to infinity of, oops, sorry, we already got that part. We don't even need that anymore, sorry. And so that just becomes, this all again just became 1 over e, and that's going to be less than or equal to 1, or just not equal to, just less than 1. Therefore, the magnitude of x is just less than e. So therefore, our radius is e. Whew, that's a tough one right there. Take a look at the algebra behind that one again. All right, the last one says The first two terms in our series are used to approximate g of 1. Use the alternating series error bound to determine the upper bound on the error of our approximation. So let's first find g of 1. Well, g of 1 would equal, starting at 0, if we let n be 0, we're going to get 1 over 5. Minus, it is alternating, n equals 1. If I plug in 1, I get 1 over 2e plus 3. And I want to find out how accurate is this, okay? So they're telling me to use the alternating series, so I'm going to set that up. The series alternates, decreases in magnitude, and the limit equals 0. Therefore, the error is less than the next term, a sub 2. And I can just plug that in. 1 over, this becomes, now it's the magnitude, so if I want to, I can do absolute value if I want to, negative 1 over 2e squared plus 3, which is just 1 over 2e squared plus 3, and that is the upper limit by the alternating series remainder. Write out that sentence. We love that sentence. I hope you enjoyed the video. I'll probably do part B for us, make that a little bit better for us. But check out the video if I do. Bye-bye.